before that, I was actually
Okay, this is good.
because then they got kicked out of that's why I actually wanted to
Okay, let's ask Vishu. So our next speaker is Shoham Sabach from Institute of Technology. So he's going to talk about also non-convex problems.
So, thank you very much. I would like to thank the organizers for their kind invitation. Very cool. So, as my title said, I will tell you about a few recent developments in non-convex optimizations, which are based on three joint works with my colleagues Amir Beck, Shoham, Thomas Spock, and Mark DeBoer. It's not all of them together all the time, so I will mention everyone in the right place at the right time. So I will begin with a description of a general framework for analyzing algorithms in the setting of non-convex and non-smooth optimization problems. You will see it's quite general, but then I will show a certain optimization model and a unifying algorithm to tackle this model. And actually this algorithm will be used to two applications. First I will show you some applications in non-negative matrix factorizations that can be solved by this unifying algorithm. Then another application for the well-studied blind image deconvolution. And I will conclude my talk with another application which will need a modification of the unifying algorithm and will be used for solving, I'm not sure that the classical is appropriate here, but for the regularized structure total least squares problem. So I will explain what is the problem later on if you are not familiar with it. So let's start with a very basic problem of minimizing a proper and lower semi-continuous function of psi, which is bounded from below. Sorry.
They are recording the video, so it's better that you put it on. Otherwise, they can catch the sound.
Okay, so let's start with a very basic optimization problem of minimizing a proper lower semi-continuous function of psi, which assume to be bounded from below. Our goal is, after we generate from a generic algorithm, calligraphic A, iteratively a sequence zk, we would like to know what is needed to show that the zk, the sequence zk, converges globally to a critical point z star. And by critical point, we mean a zero of the subdifferential, which is the classical notion, but here we need to take care that since the function is non-convex, by subdifferential we mean the limiting subdifferential was defined by Rockefeller and also Mordukhovich. There are several people that deal with this definition, and I will not get into much details, but this is the definition. So in this sense, actually whenever I say this subdifferential in the talk, I mean the limiting subdifferential, and of course if the function is known to be convex, then both subdifferential coincide and you get the classical subdifferential that Patrick showed this morning. So, as I promised, I will show a general framework for answering this question. We want the global convergence of the sequence zk. So, the framework actually consists of three main conditions. The first two conditions depend on the algorithm, the calligraphic A, while the third condition, I will get it later on, it depends only on the data of the problem. That is only on the objective function. So the first condition is requiring us for showing that the sequence of function values psi zk is a sufficient descent sequence. And actually, the decrease should be proportional to the squared norm of the gap between two successive iterations. While the second condition requires us to find one subgradient of the function, wk, which is bounded from above, again by a positive constant, ρ2, and the norm of the gap between two successive iterations. So these two conditions are quite standard when you analyze descent methods. Even in the convex setting or in the non-convex setting, these two conditions are quite standard. And the problem with these two conditions that they usually lead only to limit point convergence, which means that any limit point of the sequence is indeed a critical point, but it's not enough for showing global convergence of the whole sequence to a critical point. To get more, as I said, we will need to assume more information on the data, more information on the objective function of the minimization problem, and this will be the third step of the general framework that I would like to present. So the third step is involved what is called Kurdika-Lozachevich property, or in short, because the names are not that easy to say all the time, is the KL property. So if the function, the objective function psi, is assumed to be a KL function, then what we can show is a global convergence. But actually what we show first is that the sequence zk has finite length property, which means immediately that this is a Cauchy sequence, and therefore it's immediately a convergent sequence. So we first have the two conditions which depend on the algorithm at end, but then additional information on the data, on the objective, give us the possibility to pass from limit point convergence, which is quite classical results that can be obtained, to a global convergence of the whole sequence zk. So first of all, there are several papers that deal with KL property. It's become very popular in the last few years. And in our paper, with Shoham and Mark Tibur, when we developed this framework, so this development shows exactly which role, which mathematical tool is needed in the convergence analysis at each stage of the convergence analysis. Moreover, you see exactly the role of the KL property. As you see, we single out three conditions, and the KL property needed only in the third stage of the convergence analysis. This actually allows for anyone to take different algorithms using this framework to prove global convergence, because we single out exactly what the role of each stage of the analysis. So if you want to summarize the general framework that I discussed, then we have this theorem. So let psi be a proper lower semi-continuous function, which is bounded from below. And here we add the assumption, the KL assumption. This is the assumption that we need on the data. And assume that zk is a sequence produced by a generic algorithm satisfying conditions C1 and C2 that you saw that I presented in the previous slide. If, in addition, any limit point of the sequence is a critical point, it's another small assumption that usually can be proved, depends on the algorithm. Better? It's okay? Then you can show that the sequence zk converges globally to a critical point, z star of the function psi. So if you have the two conditions and the KL property, you can show global convergence of the sequence zk to a critical point. So this is the general framework, but as you can see, the main ingredient here is the KL property. Since the KL property is quite involved mathematical tool, I will not get into much details on that, but I want to convince you that KL functions are quite often appears in optimization. So I would like to answer the question, are there many KL functions? The answer is yes. And actually it's based on the following important results of Shoham and Aris Dianyalitis and Adrian Lewis. They showed in 2006 that any proper lower semi-continuous, which is semi-algebraic function, satisfies the KL property at any point of the domain of the function. So this results has a huge impact in practice, because checking semi-algebraicity, I remind you here the definition of semi-algebraicity, is much, much simpler than checking the KL property that I even didn't show you, but believe me that it's much simpler to checking semi-algebraicity of a function than verifying the KL. So any semi-algebraic function is a KL function. So any semi-algebraic can be used the general framework that I presented. So in order to fully convince you, I will show you a short list of semi-algebraic functions. So you see that most of the functions are quite often appears in optimization problems. Of course, all the sparsity inducing norm, the L0, the L1, functional matrices, and so on and so forth. And actually, you can generate more functions, more semi-algebraic KL functions, by using the following operations, which are all preserved the semi-algebraicity. So you can generalize sum of such functions, products, and so on and so forth. So as you can see, we have a very vast collection of semi-algebraic and therefore KL functions that you can use the general framework. And I will show you examples later on in the application that you will see that indeed we can capture a lot of important applications. Okay, so let's discuss the model. So as I promised, I want to discuss a quite general model in optimization that capture a lot of applications, but of course not all of them, but we will discuss this model. And actually the model is very simple. It consists of three functions. The first two functions, f1 and f2, are proper and lower semi-continuous. And it's important that they are separable over the blocks of variables. So as you can see, we assume non-smoothness of this function. So what we actually ask that the constraints on each block are separated. Okay, so we cannot get any coupling constraint. On each block you have a different constraint. Then you have a coupling function h, which is the third function in the model, which is indeed a coupling function, could be coupling. Otherwise it's completely a separable model. But this function should be smooth. And not only smooth, we assume that if you fix one of the blocks and differentiate the function with respect to the other block, then the partial gradient is Lifshitz continuous. So it's Lifshitz continuous if you fix one block, and it's also Lifshitz continuous if you fix the second block. But it should be important that since we are dealing with non-convex problems, this Lifshitzity does not say that the old function h is Lifshitz continuous. With gradient Lifshitz continuous, it's only true. It's true only in the convex setting. And I will show you an application later that it's indeed not the case. That we have partial Lifshitz continuous gradient, but not global Lifshitz gradient. So as you can see, in the model, non-convexity assumed not in the coupling function nor the separable function. And it's also very important to stress the fact that I present here only two blocks of variable. This is just for the simplicity of the presentation. Our general framework and the algorithms and the results that I will present soon are all valid for any finite number of blocks. I choose two just to simplify the notations and the terminology. So as I said, I will show you three applications later, but there are many more applications that can fit to this model, especially if you give any finite number of blocks, you can cover much more applications. Okay, so we have a general framework, we have an optimization model. Let's discuss the algorithm. As I said, I would like to today present a unifying algorithm for tackling this model. And I will explain the algorithm. It might be looks at the first as a bit involved, but I will explain it, and you will see that it's very simple. And the algorithm actually consists of two main steps. And as you can see, if you check it carefully, each of these two steps is exactly proximal gradient step. But with respect to the first block, we keep the second block of variable x2 fixed, and we want to do a proximal gradient step only with respect to the first block of variables. With respect to the first block, we have only one non-smooth function, which is f1. So in this, you see, we have a proximal gradient with respect to x1k. Then the alternating idea comes into play, and we fix the first block after we update this block, and we compute another proximal gradient step, now with respect to the second block. In this algorithm, we also added two intermediate sequences, the y and the z. As you can see, both sequences depend on parameters, alpha and beta. But, as I will explain soon, we can choose different settings of parameters, and then you will get different, and some of them are well-known algorithms. So, as you can see, the algorithm, we call it IPAL. It's a recent algorithm that I studied with Thomas Spock. And IPAL is to mention the inertial proximal alternating linearized minimization. So these two sequences comes to fill the gap on the inertial idea, and of course you see the alternating and you see the proximal. So this is all the ingredients in the algorithm. So indeed, this algorithm generalizes in some sense few other known or studied algorithms. First of all, if you take both parameters, inertial parameters, to be 0, which means that instead y and z, you just write the x1 or x2, depends in which block, then you recover the Palm algorithm, which was done in the same paper that we developed the general framework with Shoham and Mark. But another algorithm that can be seen as a particular case, that if you restrict yourself to only one block of variables, not two or not more than two, just one, then actually what you get is the iPiano that Joachim talked this morning. It is an algorithm of several authors, including Thomas Spock. Therefore, you see the connections between us and the algorithm. And actually, the iPiano by itself generalizes two well-known algorithms. So, first of all, of course, it generalizes the proximal forward-backward algorithm, even in the non-convex setting that was analyzed in a previous paper of Shoham and Latouche and Zweiter. So this can be done again if you have only one block and you take all the parameters to be 0. And more than that, it also generalizes the heavy ball method of Polyak from 64, that if again you take only one block, you take the non-smooth part to be 0, and actually you also take the parameter beta to be 0. So you see that a few methods can be seen as a particular case of alpha. Okay, so in general, you would say, okay, let's use the general framework that I showed before at the beginning to prove that iPiano indeed, iPal indeed converges to a critical point. But there is a problem. The iPal algorithm is not a descent algorithm. You cannot show that inertial-based methods are sufficient descent methods. The function values does not necessarily decrease at each iteration. So this, of course, cause us a lot of trouble with the first condition that asks for proving a sufficient descent. But we were able to define an auxiliary function that with respect to this auxiliary function, we do prove a descent property. And then we can use the recipe, the general framework, to prove convergence of IPAL. I will not get into much details of exactly what is the auxiliary function, but we can overcome this lack of descent by defining a good function to measure the progress of the algorithm. And then we get the following convergence result, saying that if the function is a KL function, then the IPAL do satisfies the two conditions C1 and C2. But here, in order to get the convergence, we need to restrict our inertial parameters to be between 0 and 1/2, the alpha parameter. The beta could be between 0 and 1, not a problem, but the alpha should be restricted to be between 0 and 1/2. Then you get that IPAL converges to a critical point of the problem. Okay? So, as you can see, the steps of the algorithm, I will show you again the algorithm. The steps of the algorithm depends on 1/tau 1 or 2k. So this is the step size of the gradient step. So in the convergence analysis, we got an exact formulas for the parameter tau. So the parameter tau, in the general setting of non-convex, we got the tau should be related to the Lifshitz partial Lifshitz parameter, which makes sense. As we know, usually the step size of the algorithm somehow depends on the Lifshitz constant. But here we have also the inertial parameter, the beta and the alpha. So you immediately see why we need to restrict ourselves alpha to be between 0 and 1/2, just to make it a non-negative number. But this is a very interesting remark. If the non-smooth functions fi are known to be convex, and in few, even more than few applications, however, the coupling function is non-convex, sometimes the constraints are due convex. Then we can improve the parameters tau. Actually, we get two advantages here for the same price. First of all, as you can see, I have a factor of 2 in front of the parameter. And as you remember, if I have a factor of 2, so the parameter 2 is smaller by a factor of 2, which means that I can take twice as larger steps in the algorithm because the step size is 1/tau. And more than that, you can see that here I have only 1 minus alpha, so I can take alpha to be in the extended interval of 0, 1 and not restrict myself to 0, 1/2. So we get two advantages if you have convex, and it makes sense. No free lunch. Non-convex, it's complicated. And on top of that, so this is what I mentioned. On top of that, if you don't know the Lifshitz constant in advance, which is a real issue in applications, then you can incorporate a backtracking scheme into the algorithm. I will not put exactly details, but this is you can do it. And all our convergence analysis remains valid if you put a backtracking scheme. So you don't need to know the Lifshitz partial gradient constants in advance, or even if you know them, but they are quite expensive to compute, then you can use the backtracking scheme. Okay, so this concludes the theoretical part. I will show you the general framework, the general model, and the unifying algorithm. So let's discuss few applications. And the first applications belongs to the class of matrix factorization problems. And in this class of problems, suppose you are given a matrix A which of course assumed to be non-negative, and an integer number r, which is usually much smaller than m and n. Then you would like to approximate the matrix A by finding two matrices, two non-negative matrices, X and Y, which approximate the matrix A. So accept the non-negativity constraint, we add here another requirement on each individual matrix. So we assume that the matrix X satisfies this constraint, and the matrix Y satisfies this constraint. So it's additional requirements on the solution, accept the non-negativity. So for example, it can show if you want to add a sparsity or any other regularization of the problem, you can add it in the constraint R1 and R2. So a very general optimization model that you can think of to deal with this problem is that you want to minimize a certain proximity function that measure the quality of the approximation between the original matrix A and the multiplication of X and Y, given by the function D, and of course X belongs to the constraints and Y belongs to the constraint. So this is a very broad class of non-negative matrix factorization problem. But I would like to focus here on a special choice for the proximity function, and I will take the function D to be the Frobenius norm. And then actually what you get is the very classical problem of non-negative matrix factorization. And actually the non-negative matrix factorization is in the case if you ignore the rate constraint. So all what you want is to minimize this function under the constraint that both separated matrices are non-negative. When I say non-negative, I mean component-wise. Each component in the matrix is non-negative. Here, we add the additional rate constraint, which, as I said, in the application that I will show soon, but in many other applications, it's very common to take them to be sparsity. So here, by sparsity, I take the most sparsity-inducing norm, which is the L0 norm, which measures the number of non-zero elements in a matrix or in a vector, not matter, both on both matrices. However, you can take it on one matrices and on the other not. It's since it's a parallel, it's not, you're not restricted to do all the time the same on both matrices. So if you would like to apply IPALM here, the main effort of IPALM is the computational of the proximal gradient step. And actually, the computational of proximal gradient step is the computation of a proximal mapping of the non-smooth function. In our case, the non-smooth function is actually given by the sum of two indicators. One is of the non-negative ortant, so this is thanks to this constraint. And the second is another indicator of the L0 ball with sparsity level of S. So we have sum of two indicators, and we need actually to compute the proximal mapping of this function. So in general, to compute the proximal mapping of a sum of two functions could be quite difficult. But, lucky us, we found a very simple formula how to compute this proximal mapping. And actually, because of the spatial structure of these two sets, what you can do, the computation actually reduced to the following two simple computations. First, you take the matrix and you project it onto the non-negative ortant, which is trivial task. You just cut the negative component. And then it's followed by a projection onto the L0 ball, which is defined by this optimization problem, but this can also done very efficiently. All what you need to do is to sort the vector and take the S largest entries, of course, with respect to absolute value. And therefore, you get the non-convexity because maybe you have more than different S largest eigen absolute value. So all what you do is the composition of two simple projections in order to compute the proximal mapping of F, and you can apply IPAM. Okay, so what we did, we took as an application the phase recognition problem. So suppose you are given a matrix A, which includes 400 faces, and any face is the size of 64 by 64, and we would like to solve the following optimization problem, which means we want to minimize the squared norm for Benioff norm of A, which is this database, minus the approximation of two matrices, X and Y. X holds the basis faces. So in the matrix S, what you see is R basis faces. And in the matrix Y, what you see is the basis components of each face. So each column in the matrix S is a basis face. Each column in the matrix A is a coefficient vector. And here we also assume sparsity, accept the non-negativity, which is clear. We assume sparsity on each column, which means that we want a sparse basis face. We don't want all the pixel in the basis image. We want to get a sparse and compact representation. So we have here a sparse constraint on each column. So this, of course, can be solved by IPAM. You see that in this case, if we take R to be 25, so we want a basis of only 25 faces, and we run IPAM with different levels of sparsity. So we took 25, 33, and 50. And as you can see, here are the basis faces for each different level of sparsity. And as you can see, as large as the sparsity, we get a more compact representation of the basis faces. And this is, of course, very important if you want to deal with a huge scale databases. The compact representation is very important. So actually, if you think how can we apply IPAM here, so we need to identify the matrix F1 with the indicators on the X block, which means non-negativity and sparsity on each column. And as I showed before, this can be done very efficiently. And actually, with respect to the second block, we didn't assume any additional requirements, just the non-negativity. So as you can see, in this case, the second function is indeed convex, which means that in this case, with respect to the first block, we had to take the parameter tau according to this formula, but with respect to the second block, we can take the parameter tau according to this formula. So we have different ranges for alpha 1 and alpha 2. So I will present you a small table with what you can see here is the function values of the objective function of the Frobenius norm. And what you see, it's a different number of iterations. And you see three different types of choices for the inertial parameters. Let's start with the first block. So the first block is, of course, if you take both parameters to be 0, then you recover the Palm algorithm. But if you take both parameters to be the same, on both blocks, both alpha and beta are all the same, for example 0.2, you see that you have a faster decrease of the function values. But we also saw that if you choose the parameters to I, for example 0.4, then you get worse results even than PAL. So it's not necessarily that taking the largest initial parameter will give you the best results. In the second option, we also took fixed parameters, but here, since the second block is convex, we can take double parameters. And then you can see, if you take them 0.2 and 0.4, you see, again, a faster decrease. And if you take them too large, you see, again, the same phenomena that you get worse results. The last show the best performance is if you choose the parameters alpha and beta to be dynamic, which is completely acceptable in the algorithm. But unfortunately, this choice is okay, but what we did to get this result, which looks very impressive, is we didn't choose the tau according to this formula, because if you take these parameters goes to 1, then what you will get in the parameter, that you get a very small, very large tau, which means very, very small step size. So what you see here in the last row is this choice of parameters, but tau taken as the Lifshitz constant, without the parameters in front. And then you see the best results, but unfortunately this is not covered by our theory. So all the rest do cover, but the last show the importance of inertial parameters, and we will consider it in our next work. Okay, another application is the well-studied but yet challenging blind image deconvolution. I guess you're all familiar with the problem, so I will skip all the exact details, but we are given a blurry and noisy image F. We would like to recover both the kernel and a sharp image. So a sharp image U, which should satisfy this constraint, so it should be normalized into the interval 0, 1. And the kernel should be in the unit simplex of size capital N. So as you can see here, again, the two variables of the problems are with convex constraints. Both the interval and the unit simplex are convex constraints. So the problem can be formulated using the optimization model. And what we have here, the function phi, is given by this formula, which means that this promotes sparsity on the edges of the image. So lower function values means sharper images. And here, of course, we have the fidelity term, the data fidelity term with the classical 2D convolution operations. So this, of course, can be applied by, can be solved by IPAM. Of course, here we choose the smooth coupling function to be this one, and this is the non-smooth function with respect to U, and this is with respect to B. You see both of them are convex. Therefore, in both cases, we can take the following parameters for tau. Both of them are convex, so we can use the extended interval. And you see again the same similar table with function values. But here, what you see that after a small number of iterations, actually Palm works better. Which means if you don't use inertial terms, you get lower values after a small number of iterations. But if you give it more iterations, then you get a much more decrease when you use inertial parameters. And here we see that actually, again, if you give it 0.4, we get the most decrease. Again, the last line is just to motivate us to keep checking what happens if you choose these parameters, and it again gives the best performance. So what we tried is to find the blur and a clean image from the original book image. That here you see the convolved, and here you see 3 results obtained by the algorithm. And actually the first result, which is quite, actually here they all seem more or less the same. This is not really the case in the computer, but as you can see with Palm, we get a much worse result than what we get with inertial term, with this one, and of course with this one. So we indeed got a much better recovered kernel and recovered image. You see the kernel here recovered quite actually very good, and here not much. So you see that the inertial terms indeed give us better performance also in the convolution and also in a faster decrease of the function values. Okay, the last application that I would like to discuss is on the regularized structure total least squares. So I'm not sure that you are all familiar with this application. Therefore, I will give a short introduction. What is this problem? So in order to do that, we will need to see few classical models for solving or for approximating linear system of equations. So we know that a wide variety of applications lead to the study of approximate linear system of the form Ax is approximate to B. But in many scenarios, we know that both the model matrix A and the right-hand side vector B are subjected to some noise. And in this case, the equation actually should be written like that. We add a noisy matrix E to the left-hand side, and we add a noise vector W to take the noise in the vector B. So of course, both matrix A and vector W are unknown in advance. And in this case, the classical total least squares model seeks to minimize the squared norm of the perturbation matrix E plus the squared norm of the error vector W, or you can write it as this equation. So this is the classical total least squares problem. However, in many scenarios, the model matrix A, known to have some linear structure. And in this case, it's very natural to assume that also the perturbation matrix E share the same structure. So if the matrix A has some special structure, it makes sense to assume that the perturbation, the noise, also share the same structure. So in this case, we get what is called the structure total least squares problems, which in this case, we would like to minimize with respect to two vectors of variable. First of all, the vector x, which is obvious, is the solution that we want to find. And here we have another vector, the vector y. And what is the vector y? The vector y is the vector of components which fits to the structure of the matrix. So yi are the component, the structure component, which are unknown, while the matrices, the component matrices ai, are known. So we have two vectors of variables, x and y, and we would like to minimize the sum of these two functions. Okay. Lastly, as you can see, we get progress until the regularized structure total least squares problem. A very common phenomena in the solution of linear inverse problems is that sometimes the solution has a huge norm. This is mainly because the situation that the model matrix A is ill-posed. In this situation, you would like to control the solution by adding some regularizing function. And then actually, if we take the structure total least squares problem and we add a regularizer to control the norm of the solution x, we get the problem regularized structure total least squares. So the problem, as you can see, f is a non-smooth, and here we assume convexity. However, the general framework that I showed you before can be go through with f non-convex, but we wanted to use a specifically regularizer, the TV regularizer, so this is a convex one. And here we also add the standard deviation. This is just for the applications matter. From optimization point of view, it's not changing anything. So of course, what you have here is a non-convex, non-smooth problem. You see again that you have some coupling function which are differentiable with continuous Lipschitz continuous partial gradients. But as you will see later, this model has some very nice structure which allows us to develop a variant of IPALM or PALM to deal with this problem. So before showing you our algorithm, I want to discuss a classical classical algorithm to deal with RSTLS problem, and actually the algorithm is not exactly solving the model that I showed before. They consider a bit different model. So this was done by Prusner and Olari, and they consider the following model, which is a bit different than the model that we consider. They would like to minimize the norm of the extended matrix. So they allow for three different kinds of norms, L1, L2, and L infinity. And as you can see, here we have the data fidelity term. Here we have the error matrix. And here we have the regularizer. So they put all of them together in one matrix, and they want to minimize the norm of this matrix. Okay. So their method is actually a variation of Gauss-Newton method, which means that you take the function inside the matrix and linearize this function with respect to both variables x and y around a given point x bar, y bar. So what you see here is the derivative of this function with respect to x and with respect to y. And of course with some constant. So at every iteration of their method, which they called STLN, structure total list norm problem, they have to solve a linear system of equations. So actually, this is not really a method because it's two nested schemes. Because on each iteration, you need to solve this subproblem. So of course, if you take the situation when the L2 norm, then the two models, of course, if you take the square of the norm, then two models you can separate and you get exactly the model that we consider. But if you take the L1 norm or L infinity, you get completely different models. And of course, we're not dealing with these models. So as you can see, this method, their method, has few drawbacks. First of all, the model. There is a problematic issue with the model. The model shares the same norm for the data fidelity term and the regularizer. This is a situation that usually we want a different norm for the data fidelity and for the regularizer. But in their model, it must be the same norm. More than that, the algorithm, it's a Gauss-Newton from the outside, but at each iteration, you need to solve a linear system of equation for the inner iterations, which of course is a nested scheme, which causes a lot of numerical and accumulations of error. On top of that, there is no any convergence results for their algorithm. I know that we are dealing with non-convex, but even a critical point convergence was not proved. And on top of that, from the applied point of view, their problem cannot be applied for large-scale problems because they need to solve at each iteration a huge-scale linear system of equations. This is a major drawback. And actually, all these drawbacks motivated us to consider a very simple, with a low computational effort algorithm, of course, with a provable convergence theory using the general framework I mentioned at the beginning. So we call this algorithm a SPA, semi-proximal alternating approach. And this is because, as you can see, with respect to x, what we have a non-smooth function plus a smooth coupling function. So as in Palm or IPalm, we can tackle this sub-problem using a proximal gradient step. But then there is a change. There is a different than Palm, because if you look with respect to the y variable, you have the sum of two quadratic functions. So why to approximate the solution of this problem when you can solve it explicitly? And more than that, it's important that the p, which is the number of the components, is usually very small number, which means that we can solve explicitly exactly the problem with respect to the block of variable y. This can be done accurately and efficiently since p is usually very small. And actually, the only effort is when you choose different regularizer for the X block. This is all the efforts to the computation of the proximal map. Okay, so we consider an example from the blurring of large scale. We took the classical image of the cameraman. We applied a Gaussian blur and standard noisy. And it's important, according to the model, we didn't use the transformation P in the algorithm. We of course used a noisy version. This is exactly the model of the regularized structured total discourse. We don't know exactly the transformation, but a noisy version. And we took as regularizer the TV. This is the exact parameters, and this is the classical TVL1 regularizer. So you see, just illustrating example, you see the original, the blurry noise image, and you see that after applying SPA with 50 iterations and 2 other iterations, we get a very nice recovery of the image. And actually, we cannot compare our method here with the RSTLN, first of all, because the model does not fit to their model, because we have a different norm for the data fidelity, the 2 norm and L1 for the regularizer. And on top of that, we tried on a much smaller problems. The RSTLN works quite slowly, so it will take much more time for these images. Okay, so my talk based on 3 papers, as I mentioned at the beginning. These are the 3 papers, and thank you very much.
I have 2 questions. The last one is, I think the last slide you showed. Yeah, this one. I didn't understand very well the ill conditioning level of the blur you applied for this kind of image. Which kind of blur?
Yeah.
It's 5 by 5 times 5 is the dimension of the,
Yeah.
and the standard deviation of the isotropic Gaussian.
Yeah.
So it's almost uniform.
Yeah.
Okay. So it's not very ill conditioned, this kind of blur, right?
Yeah.
Okay.
Yeah,
But I don't think it's a problem for the algorithm.
No, just illustrating examples. Didn't put here all the numerical examples. So.
Yeah. The other question was on the very interesting blind blurring case, in which you showed, similarly to what Fiorella showed in our case of non-convex, in which you converge to 2 different, by using inertial or not inertial, you converge to 2 different estimation of both the clean image and the blur kernel, right?
Yeah.
And they have different quality.
Yeah, you see.
So I think the observation of Mila is true also in this case, in the sense that you use an algorithm for a non-convex optimization, and you converge to 2 different local minimizers.
You're never sure. That
You are never sure of. Okay, it is good. I look at it.
No,
right?
it's just when we look at it, we see that it's better.
Yeah. Okay. Good.
Also, the function values here says that it's smaller, but of course, it's never
It's
saying
more,
that smaller function values means better.
Okay.
When we're dealing with non-convex problems.
Yeah.
It's
Good.
Not clear.
Good.
Are you saying for this blind deconvolution probe using IPAM, you can prove you can convert to the global minimizer?
Global.
I wish.
I think I know that.
Global
But you use the
I
same
need to keep
algorithm.
something for next time.
And you said you converge globally. Right?
That's right.
That's the confusion. So
No, globally I mean the whole
Yeah,
sequence,
you
not just
always-
subsequences.
Oh, I see.
Not
Sorry.
globally.
I mean the whole sequence. No, not global minimum, of course.
We will give you the fields method.
Yeah.
So can you go to this proximal map formula?
Yeah.
Proximal map formula. I have a
For
question.
the
Page 52. So here, so is this the operator TS and P plus, are they commute? And put the PS and the P plus?
If I'm not wrong, yes. You can compute, you can commute, and you will remain. If I'm not wrong, you're right.
Yeah, because for
This
the
is a
F,
very particular case.
but because of F, you have two projection, right? So
Yeah, but the projection onto the intersection is not necessarily the composition of the projection. In general, it's not true.
yeah, but for the F, because there is a two delta function, right? Sum of two delta functions, so you can put
two indicators.
yeah. So they, I mean, in that case, you can put one before the other, right? And then when you solve it, then it's now
No,
it become
this order does not affect this order. It's just I can write a different
yeah.
order.
So,
It
but
will be
then
the same
now
function.
here, it's the same function, but now
I
when
think
you,
here,
yeah.
because of the special structure of the non-negative order and the L0 ball, I think it's also true if you take the opposite order, but I'm not sure.
Okay.
No.
No,
No, it's not.
no, there is a case.
If U is very large negative at some point, then you should not see it. So
No, so there, no, so there is with the L2 ball, maybe it's true. There is a case that it's true that with the maybe L2 ball is true. No.
Okay. But it's not related to this, yeah. So.
No, it's not related to this.
Yeah, okay,
Because anyway, you put this sum in the optimization formulation.
Because
so the order does not change anything.
Yeah. Okay.
Yeah.
I don't see why in this phase problem the positivistic constraint is relevant. But I mean, it has nothing to do with your problem.
Yeah, it's the way that you choose the components.
Why? Because you are adding. I mean, the components seem to be eigenvectors you are adding. So why should they be?
You're asking a good question. I don't know the answer. I'm not dealing exactly with phase recognition. It's just application, but it's a very classical application of non-negative matrix factorization. So I guess there is a reason, but
If you represent the whole phase, I understand because it's
the other side.
a gray level. But if it's just the phases you add up, then there should be.
I don't want to say something that is wrong.
What was the question? What was the question?
I think why the phase element should be
Maybe someone
positive.
of you more familiar with it.
To be interpretable as part of the sense, so that they can combine. That's the,
Add the
that's
9 to let's put the 9.
the motivation.
You need to add some intensity.
Maybe, I mean, when you can add like some negative part and then some positive, and that gives you your I with the individual parts you
Exactly.
somehow.
That's the motivation.
These are
Not
very-
non-negative.
I mean,
No, it's a bit mysterious.
I think it's just a model, it's assumption. I just want to.
You have any consensus? No. No. Then okay. Any other questions? No. Then let's. Okay, so this ends today's session, and so we resume tomorrow at 9:30, and then again at 9 there will be a breakfast. Yeah.
It's not the subtraction that you could get higher.